Okay, chapter 11, section 2, inference about two means dependent samples. Objectives: test the hypothesis for a population mean from matched pairs data. Construct and interpret confidence intervals about the population mean difference of matched pairs data. Objective number 1, test hypothesis for population mean from matched pairs data. So note, these are dependent samples. Matched pairs data. Statistical inferences methods on matched pairs data use the same methods as inference on a single population mean, except that the differences are analyzed. To test the hypothesis regarding the mean difference of data obtained from a dependent sample, that is matched pairs data, use the following steps provided that the following are satisfied. Number 1, the sample is obtained using simple random sample or data result from a matched pairs design experiment. Review chapter 1, what that means. Sample data are dependent, they're matched pairs. As a quick review, whatever subject is selected for one sample determines what's going to be selected for the second sample. In the end, you're going to have equal size samples, and in the end, whichever one you pick, there should be a correspondence to one in the other sample. So a one-to-one correspondence. The differences are normally distributed with no outliers, and the sample size n is large, that is greater than or equal to 30. Sample values are independent. So sample size is not just random, but it's no more than 5% of the population size. Summary of all those things: the sample is obtained from simple random sampling of the data resulting from matched pairs data or matched pairs design experiment. The sample data are dependent. The differences are normally distributed with no outliers, or and sample size is large, that is at least 30. Sample values are independent, that is sample size no more than 5% of the population size. The convention. Since this is a matched pair study, the sample size for each sample is the same. N is equal to N1 is equal to N2. Normally, the null hypothesis would involve equality. So H naught is equal to or represents mu1 is equal to mu2. But since the sample sizes for both are the same, we can combine the two into a new expression. Here's the null hypothesis. We subtract mu2 from both sides. We get a difference on the left and 0 on the right. So now the null hypothesis represents mu1 minus mu2 is equal to 0. Because the same sample size for each, we can define a new figure, mu d, d for difference. So mu d is mu1 minus mu2. Then we have a new form of the null hypothesis that H null represents mu d equal to 0. If you're not sure, one way to think about it is that these mu's are in alphabetical order, not are in numerical order. So mu1 minus mu2. The one comes first, the second comes second. Testing hypothesis regarding the difference between step 1. Determine the null and alternative hypothesis. The hypothesis can be structured in one of 3 ways, where mu d is the population mean difference of the matched pairs data. Notice we have this. In each case, the null hypothesis is the same. Mu d is equal to 0. Two-tail, mu d is not equal to 0. Left tail, mu d is less than 0. Right tail, mu d is greater than 0. Step 2, select a level of significance depending on the seriousness of making a type 1 error. Compute the test statistic. So T naught is equal to this expression, which simplifies to this at the end. Please note that in the denominator, that denominator fraction is one item. So you're not going to take D naught divided by SD divided by square root of N. That would give you the wrong value. It will be D bar divided by the quantity of S of D divided by square root of N. Anyway, this T naught follows a student's T distribution with N minus 1 degrees of freedom. The values of D bar and S of D are the mean and standard deviation of the difference data. Note, with T naught, we have the general expression for the T distribution. We replace them with the values for this difference distribution. The X bar now becomes D bar. The mu becomes 0 because remember the null hypothesis is mu of D is equal to 0. The S now replaced with the standard deviation of the difference data. Square root of N remains as is. And simplify that, we get this expression here. And if you do want to simplify it to get rid of the multiple fractions, it gets simplified into this expression, D bar times square root of N, all divided by standard deviation of D. The D bar is a number. The S of D divided by square root of N is a fraction. Going back to arithmetic, a number divided by a fraction is equivalent to the number times its reciprocal. That is the flipped version of that fraction in the denominator. And that's where that other expression comes in. Step 3, in the classic approach, we use table 7 or a calculator to determine the critical values. Here are the scenarios, the two-tail, left tail, and right tail. The critical values, remember with the two-tailed, the alpha is equally invested in both tails. Left tail, the alpha is totally invested in the left tail. Right tailed, the alpha is totally invested in the right tail. Those are the representing alternative hypotheses. Compare the critical values to test statistic. With the two-tailed test, is T naught less than the negative of T of alpha over 2, or is it greater than the positive T of alpha over 2? Left tail, T naught is less than the negative of T of alpha. Right tail, T naught is greater than T of alpha. In any of those scenarios, you would reject the null hypothesis. And then at the end, you're going to state the conclusion. In the p-value approach, we're going to use table 7 to approximate the p-value. Remember, the test statistic now generates the boundaries for our regions. For the two-tailed test, we look at that arrangement there is just to guarantee that we have a positive value on the left and a negative value on the right, using that absolute value, because we don't know what T naught will be. It could be positive, it could be negative. So irrespective of the sign, if you take the absolute value of it, you have the positive value that we're looking for on the right. You take the negative of the absolute value. Now it's guaranteed to be negative to represent the left tail. Notice the p-value is going to be the sum of the areas, which is really, since because of the symmetry, that's going to be twice the area on the right. P-value on the left tail is just the area to the left of our test statistic. Right tail, our p-value is the area to the right of the test statistic. If the p-value is less than alpha, then reject the null hypothesis and then state your conclusion. These procedures are robust, which means that minor departures from normality will not adversely affect the results. However, if the data have outliers, the procedure should not be used. Example number 1, testing hypothesis regarding match pairs data. Professor Andy Neal measured the time in seconds required to catch a falling meter stick for 12 randomly selected students, dominant hand and non-dominant hand. Professor Neal wants to know if the reaction time in the individual's dominant hand is less than the reaction time in his or her non-dominant hand. A coin flip is used to determine whether reaction time is measured using the dominant or non-dominant hand first. What the researcher is trying to do is not establish any particular pattern in his research. Doing the dominant hand all the time first could skew the readings a little bit. To try to make it as unbiased as possible, you're going to use a coin flip to determine which gets measured first. The data obtained are presented in table 1 on the next slide. Here is the table. 1, xi represents the dominant hand, yi represents the non-dominant hand. I represents the student. So student 1, student 2, student 3. So student 2, the speed in the non-dominant hand was 0.202. The speed in the dominant hand was 0.210. We compute the differences because now we have a 1-to-1 correspondence between each piece of data. The key thing tying the two together is the student who has the hands. The top row, this 0.177 corresponds to this 0.179. Student number 7, 0.160 corresponds to this 0.194. We compute the differences. Di is equal to xi minus yi, the time of the dominant hand for the ith student minus the time of non-dominant for the ith student. We expect these differences to be negative. We want to determine if mu of d is less than 0. Here's the modified version of the table. We added a new column called difference, and it's just going to be the second column minus the third column. And we have a few negatives and even fewer positives. Now we're going to find the d bar, which is going to be the mean of all of these 12 differences. The sum of all of them is going to be negative 0.158. Compute the mean and standard deviation of the differences and obtain d bar is equal to negative 0.0132 and standard deviation of d is equal to 0.0164, each rounded to the 4th decimal place. Verify the data comes from a population that is approximately normal with no outliers. The figure on the next slide shows the normal probability plot and the box plot of the difference data. There's the normal probability plot on the left. There's the box plot on the right. The box plot shows no outliers. If we work it out here, the correlation between the difference data and the expected z-scores is 0.978. Because 0.978 is greater than 0.928, the cutoff recorded in table 6 with n equals 12, it is reasonable to conclude the data comes from a population that is normally distributed. Step 1, Professor Neal wants to know if the reaction time in the dominant hand is less than the reaction time in the non-dominant hand. So this can be expressed as mu of D is less than 0. We have the null hypothesis representing mu of D is equal to 0 versus the alternative hypothesis representing mu of D is less than 0 seconds. The test is left-tailed. We have a level of significance of 0.05. 95% confident, so that means the difference is 5%. We have our sample mean of negative 0.0132 seconds and the sample standard deviation of 0.0164. The test statistic, it gets plugged in, and we get this negative 2.788. And even if you tried it with the alternative formula, you will still get that expression there. Step 3, because this is a left-tailed test, determine the critical value at alpha equals 5 level of significance with 11 degrees of freedom to be negative t of 0.05 is equal to negative 1.796. Technically, the table gives t of 0.05 being positive 1.796, but that is okay if it were right tail. Given the symmetry of the t distribution, though, we can adjust it for the left tail test. We have the negative of this positive value to give us our negative value. There it is in the table, 11 degrees of freedom on the left. On the top, you have our 0.05 being highlighted, and where that row and column intersect, you have your 1.796. With the T calculator and StatCrunch standard mode, we have the following: fill in and adjust the highlighted fields. The outcome comes out to be negative 1.758848, which rounds off to negative 1.796. So no difference. So the test statistic, we have our test statistic of negative 2.788. Because the test statistic lies in the critical region, we reject the null hypothesis. There it is. Our alpha generates this negative 1.796, and the region to the left of it, our test statistic is in that critical region. We're in a position to reject the null hypothesis. Step 5, the sample data provides sufficient evidence at alpha equals 0.05 level of significance to conclude the reaction time in the dominant hand is less than the reaction time in the non-dominant hand. P-value method, again, we're going to calculate the test statistic, negative 2.788. Because this is a left tail test, the p-value is in the area under the t distribution with 11 degrees of freedom to the left of the test statistic, which is negative 2.788, as shown in figure A on the next slide. That is, p-value is equal to the probability of t being less than t naught, which is equal to the probability that t is less than negative 2.788 with 11 degrees of freedom. Because of the symmetry of the t distribution using table 7, the area under the t distribution to the left of negative 2.788 equals the area under the t distribution to the right of 2.788. The p-value of t being less than 2.7 is equal to the probability of t naught being greater than 2.7, figure B in the next slide. Our scenario that we want, positive equivalent that we have. So A represents the scenario that we want. B represents what we have available to us from the table. Using table 7, we find the row that corresponds to 11 degrees of freedom. The value 2.788 lies in between 2.718 and 3.106. The first value, 2.718, has an area of 0.01 to the right under the T distribution with 11 degrees of freedom. The value of 3.1 corresponds to an area of 0.005 to the right of the T distribution with 11 degrees of freedom. Here it is on the table. You would start here, go to here, and then go up and read off the area in the right table. Because 2.788 is between 2.718 and 3.106, the p-value is somewhere between 0.005 and 0.01. So 0.005 is less than the p-value, which is less than 0.01. You want to use a calculator using StatCrunch calculator. Fill in and adjust the highlighted fields. 11 degrees of freedom. We're looking for x less than or equal to 1. Well, the 2.788. The outcome becomes this 0.00882478. That rounds off to 0.009. Rounded to the third decimal place, just like all the other t-scores here. Using StatCrunch, we find that the p-value of 0.009 is consistent with the earlier inequality of 5 less than p-value less than 0.01. Here it is in StatCrunch, the same exercise, and notice the mu of d is mean 1 minus mean 2. Degree of freedom, the standard error. There's our t statistic, our test statistic, and our p-value 0.009. Step for the p-value of 0.009 or by hand, p-value between 0.005 and 0.01 means that if the null hypothesis that the mean difference is 0 is true, we expect the sample mean of negative 0.0132 seconds or lower in about 9 out of 1,000 repetitions in this experiment. The result we obtained are not consistent with the assumption the mean difference of the reaction time between the dominant hand is 0 seconds. Between the dominant and non-dominant hand is 0 seconds. Step 4, simply put, because the p-value is less than the level of significance, Professor Neal rejects the null hypothesis. And then step 5, the sample data provides sufficient evidence at alpha equals 0.05 level of significance to conclude that the reaction time in the dominant hand is less than the reaction time in the non-dominant hand. Objective 2, construct and interpret the confidence intervals for population mean difference of matched pairs data. Same idea, different format. Instead of looking at test statistics, p-values, or anything like that, we'll construct a confidence interval and go that route. Confidence interval for matched pairs data, a 1 minus alpha times 100% confidence interval for mu d is given by these. Lower bound, hopefully this kind of looks familiar. Lower bound is d bar minus t of alpha over 2 times s of d divided by square root of n. Upper bound, same thing, but you have, instead of a minus t of alpha over 2, you have a plus t of alpha over 2. The confidence interval for matched pairs data, the critical value t of alpha over 2 is determined using n minus 1 degree of freedom. The values d bar and s of d are the mean and standard deviation of the different data. Note the interval is, first of all, exact when the population is normally distributed. And number two, it is approximately correct for non-normal populations, provided that n is large. Using data from table 2 repeated in the next slide, construct a 95% confidence interval, estimate the mean difference of mu d. Here's all the data. This is a repeat of the earlier table. Column 2 is the speed of the dominant hand. Column 3, the speed of the non-dominant hand. Column 4 is the difference of the speeds. Step 1, we compute the difference data and verify they come from a population that is approximately normally distributed with no outliers in a previous example. Step 2, we computed the sample mean difference d bar to be negative 0.0132 and the standard deviation of the difference S of d bar to be positive 0.0164 and based on a previous example. Here's the T of alpha over 2 based on the table. The alpha gets cut in half, so that's 0.025. There's our column of 0.025. To the left, we have our 11 degrees of freedom, and where that row and column intersect, we have that 2.201. Using T-calculator and StatCrunch with 1 minus alpha or 0.95 and 11 degrees of freedom, we get this. Fill in and adjust the highlights. Actually, there's nothing to adjust. They're just fill in. I'll fill in the highlighted fields. The only thing we're interested in is the positive result of 2.201. Now, taking all of those values and substituting it into formula 1, we find this. There's the formula. Plugging in all the values, we get this. We simplify it, and we get this negative 0.0236. Upper bound, similar. There's the formula, plug in the values, and we still have a negative 0.0028. We are 95% confident the mean difference between the dominant hand's reaction time and the non-dominant hand's reaction time is somewhere between negative 0.0236 and negative 0.0028 seconds. In other words, we are 95% confident the dominant hand has a mean reaction time that is somewhere between 0.0028 and positive 0.0236 seconds faster than the non-dominant hand. Because the confidence interval does not contain zero is not in the picture, the evidence suggests the reaction time of a person's dominant hand is different from the reaction time of the non-dominant hand. We are 95% confident the mean difference between the dominant reaction time and the non-dominant hand's reaction time is between negative 0.0236 and negative 0.0027 seconds. If we look at the results, we have our lower limit and we have our upper limit. Because the confidence interval does not contain zero, the evidence suggests the reaction time of a person's dominant hand is faster from the reaction time of the non-dominant hand. That does it for 11.2. Let me prepare the next section here.